This is columns part 7. In columns part 6, you may have noticed I told you something wasn't right. I told you that .074 inches was the distance between the centroid line and there. It's really the distance between there and there. And I did catch that in that video. If you watch my videos long enough, you'll see me correct my mistakes, at least the ones I catch anyway. So we had to cut the last video, part 6, short. We'd figured the moment of inertia contribution of this part of the L above the centroid line. We figured it was 0.00011328 inches to the fourth. We figured the moment of inertia contribution of this part of the vertical part of the L below the centroid line. It was this one. It was 0.000021367 inches to the fourth. So now we're going to figure the moment of inertia contribution of this last part. Okay, it's 0.185 inches all the way from there to there, but we're talking about this part. We've already done that. That was part of that. So we're doing from there to there. And that was 0.143 inches across, right? Let's look at the math here. Okay, we're calling it this, our moment of inertia with that shape, the bottom part of the L. It's the integral of all the little di's there that we're going to look at, which is the integral of all the little dA's that we're going to look at, times the square of their distances from the centroid line. Okay, so our limits of integration are, we're integrating from this distance, from the centroid line to the top of this bottom part of the L. We're integrating from that distance to this distance, integrating from there to there. So we're going to take all these little areas, these little dA's, okay, and integrate them from there to there. So dA is 0.143 inches across times dy. Remember that? It's 0.185 from there to there, but it was 0.143 from there to there. So 0.143 inches times dy would be the thickness of our little incremental unit of area that we're integrating an infinite number of between there and there. Excuse me, I had to go answer the door there a second ago. So our little incremental unit of area, let's draw it here. It goes all the way across there and it's ever so thin and goes back there, and we're going to call this y from there to where our incremental unit of area is, and the thickness of that is going to be just like it was up there, dy. So our little dA here is going to be that distance, which is 0.14365 blah 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 inches times dy. So here's the math for it. Okay, and this distance from the centroid line to here is that one, 0.0742255. That's why we have that as our first, as one of our limits of integration. And this distance from the centroid line to the bottom here is that distance, which is 0.115658 blah blah blah. So that's why we have that number up here. We're integrating from there to there. Okay, so we have our length of our L, 0.143 times dy, give us the thickness of our little dA times y squared. Well, the integral of all this, that's a constant, so we have the integral of y squared dy. Integral of y squared dy is y cubed over 3. So we plug and chug with that number and that number, same numbers here. Plug that in for y, multiply it by itself a couple of times to get that cubed, multiply it by that, divide it by 3. Write that number down somewhere, put it in memory, store it. And we take this number, to the third power, multiply it by that, divide it by 3, see what it is, and subtract it from what we got when we did the same thing with that number, and it gives us this number, 0.000054501 inches to the fourth. So now we take our three contributions, our contribution of the top part of the L above the centroid line, the vertical part of the L below the centroid line, and the bottom part of the L. We just add that number, and that number together to get a total moment of inertia of 0.000113208 inches to the fourth. I told you something wrong again. When you add that number plus that number plus that number, you get this number, 0.000189076 inches to the fourth. Now is a good time to remind ourselves that we calculated the moment of inertia of our L here, which was half of the U that we originally started out with. We could double the moment of inertia of the L to get the moment of inertia of the U. We could also double the cross-sectional area of the L to get the cross-sectional area of the U. Both the L and the U will have the same radius of gyration, the same radius of gyration about the horizontal axis anyway, about this axis, the weaker axis, the one that's going to fail about. Okay, the formula for radius of gyration was, they used the letter K for it. It's the square root of the moment of inertia divided by the area. We just determined when we finally added those three numbers up right a minute ago that the total moment of inertia of this L was 0.000189 blah 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 inches to the fourth. Okay, and the area of this L is 0.019 19,000ths of a square inch. So we take that number and divide it by that number, and then we take the square root of it. It gives us this number. That is our radius of gyration. That's the number that we spent the last several videos trying to find. And the reason we want that number so we can plug it into this equation. Remember ASSAKF, ASSAKKAF.com, where we got this formula for figuring out our column strength, the formula that worked, the formula that accurately predicted how strong this tail boom was. It said, well, first off, we have to find our lambda C. Well, it's a different kind of K. That K is talking about how the ends of the column are held in place. Let's just change this K. Let's call it R, because it's radius of gyration. That letter is used for radius of gyration also. Sometimes they use K, sometimes they use R. Okay, so there it is. K was, it was 0.5 theoretically, but ASSAKF he recommended 0.65 for a little bit of a safety factor, I suppose. L was the length of our column, or the length of our segment of the tail boom that buckled, and that was 13 inches. Okay, well, R is our radius of gyration, square root of I over A, which was that number. So we stick that number there, and that'll be inches. I didn't write the inches there. Maybe I should have. There we go. And there's pi. It goes down there too. Times the square root of Fy over E. Well, Fy, you'd think, oh, force. Nope. That's a stress. It's 36,000 psi. That's the yield stress of this material. Maybe. Sometimes it's 50, but I just threw in 36 and it works. Okay, and this E is the modulus of elasticity, Young's modulus. Some say 29 million, some say 30 million. That my college physics book said 30, so that's what I'm going with. So anyway, the square root of 36,000 over 30 million, and they're both psi, so this will have no units. So we have lambda C equals just multiply it all out and you get that number right there. And now we come up to this part of the equation, or this different equation anyway. This one here, the critical stress, that F is not force, it's stress. The critical stress is 0.658 to the lambda c squared power. That is, if lambda c is less than 1.5, and it is, it's 0.936. So we'll use this equation. Remember, he had two of them, and when lambda c was 1.5, both equations gave you the same thing, because 0.658 to the 1.5 squared power, which is the 2.25 power, was equal to, what was it, 0.877 over 2.25, something like that. That was in a previous lesson. But anyway, our critical stress is this to the that power squared times our yield stress, 36,000 psi. So we plug and chug with those numbers and we get nearly 25,000 psi for our critical stress. That's what it should buckle at. Okay, so in our area of our U, not the L, but the whole thing, the U, was 0.038 inches squared. So we multiply that area times that number of pounds per unit area, we get that many pounds. 953 pounds is what ASACAF, his formula, predicted that this component should be able to withstand. This mock-up tail boom of the steel stork was loaded to 168 pounds before it finally collapsed, and that was about 73 inches away from where it collapsed. And the top flange was 6 inches above the bottom flanges, two bottom flanges. It was triangular. So the ratio of 73 to 6 is the ratio of that force to the force that is shared by the two compression members. There we go. So the actual load in one compression member was 168 times that ratio of 73 over 6. Divided by 2 because there are two compression members, and do the math, and it's 1,022 pounds. So the actual load divided by the calculated load was 7% more. It actually withstood 7% more than this formula said it should, but we should expect it to be a little stronger because we used a square L to do our calculations. And we actually had a curved one, which was a little more vertical and a little more horizontal. So we'll get back with the rest of this in part 8.